Hey everybody, Miss Bodechon here. Today we're going to look at 7F of our AKS portfolio. It says, I can analyze and interpret data to explain the flow of energy during the phase changes using heating and cooling curves. So the very first thing that we need to look at are the phase changes. You guys have learned this before, but I want to get it fresh in your mind so that we can remember all of them. So we're going to start up here with a gas. If a gas goes into a liquid form, we call that condensation. If a liquid goes into a solid, we call that freezing. You can see it's freezing like into ice cubes. This is just a demonstration with water because we're all very familiar with water, right? And then if a solid were to go to a gas form and not turn into a liquid along the way, we call that sublimation. This happens with like dry ice, okay? We have like a chunk of carbon dioxide and it sublimates into the air and turns into a gas. Now, if we're going backwards and we have a gas turn straight into a solid, again, it's skipping the step to turn into a liquid, right? It would be called deposition. This happens a lot in clouds. So if you have like a cloud full of gases and it will all of a sudden get to a really low temperature, the water vapor will solidify into crystals and then it can fall down to earth, right? If we have a solid and we move towards a liquid, we call that melting. If we have a liquid and we move to a gas, we call that evaporation. Now, if we go from a solid, liquid to gas, we are applying heat and we are applying energy, right? We're adding it to our system. If we go from a gas to a liquid to a solid, we're removing heat or removing energy from our system, okay? So if we look at our graph on our AKS portfolio, it says, label each line segment as the energy and heat are added above the line on the graph. And then it says label each line segment as energy and heat are removed under the line on the graph. So we're taking all of those phase changes and now we're going to label them where they go on this graph. So the first thing we need to do is look at our graph. What is it showing us? It's showing us time going by on our x-axis in minutes. Okay, and it's showing us on our y-axis temperature in Celsius increasing as it goes upward. We see a line on the graph, several line segments all put together, and now we have to determine which one is which. So we know as we go up, we're applying heat. So the top one should be our hottest one, right? Which is going to be a gas. We know the bottom one should be our coldest one, which should be our solid, and the middle one then should be a liquid. So what do these other two lines represent? These other two lines represent our actual phase changes, which is what's happening in the middle of them, our freezing and melting and condensating and all of that. So let me show you what this looks like completed. So here we go. Let me move myself here. So we're applying heat, we're applying energy in this direction, and then we have temperature increasing over here on this side, and what we have is our solid at the bottom. So we are starting as a solid, we're increasing temperature, we're increasing that kinetic energy and the heat, and then we're going to reach what's called our melting point. And as soon as we reach melting point, we do not change temperature anymore. Notice our line is now parallel with our x-axis, so there is no temperature change on this line as we're melting. So think of it as like solid chunk of ice. All of a sudden we're at melting point, and that ice is going to start to melt and form a little puddle underneath it, and it's going to remain that same temperature until every last bit of that ice cube has melted into a liquid form. As soon as it's all melted into a liquid form, this is the portion that you see. We can now apply heat and energy, and it can raise that temperature of that liquid until it reaches the boiling point. As soon as it reaches boiling point, the temperature again will stop, and you can see that represented by this parallel line. So our kinetic energy is now at a halt. It's still moving, right? And boiling water would be moving really quickly. So our molecules inside of it are moving very rapidly. But what's really happening is it's going to start changing that liquid water into water vapor, right? Or steam. And so you're going to have some boiling water and you're going to have some vapor all at the same time. Like if you make macaroni and cheese at home, you can see that on your stovetop, that boiling water, and over top of it is the steam. So that's the vaporization phase. And then as soon as every drop of water in the pan is gone, right, and has vaporized into the air, that's when our gas can start to increase temperature again. It can start to increase that energy, and it can get hotter and hotter. We can do the same thing in reverse, okay? So we can take the gas and we can cool it down. We can remove the energy, remove the heat, and it will do that until it reaches its condensation point. At that time, the temperature is going to stay the same, and it's going to have part of those gases collecting droplets and forming liquid, like if you've ever seen dewdrops on leaves in the morning, things like that, or condensation on the side of your cup. If you have like ice in your cup and you touch it and your hand's all wet, that's condensation, right? It's going to stay there until all of that gas has condensated. As soon as that occurs, we're going to have the liquid, and at this point we can remove heat, we can remove energy, we're decreasing our temperature until we reach our freezing point. And our freezing point is where we are going to, again, stay the same temperature until all of our liquid has solidified into ice, right? So this point we're going to have part liquid, we're going to have part ice forming, more and more forming as we go along, until every little droplet has turned into a solidified ice cube. And then we can still remove more energy and remove heat, and it can become colder and colder as we go along. So what I really want you to see is melting and freezing occur at the same temperature. Look, isn't that crazy? Vaporization and condensation occur at the same temperature. And if you think about that for a second, it makes sense, but it's kind of weird at the same time. So I want you to pause and really think that through. Ask me some questions if you don't understand. All right, let's look at our next one. This next one says, what line segments have the average kinetic energy remain the same? So we know from our last one that the average kinetic energy is just the motion of our molecules. So where are they staying the same? It doesn't say where do they stop, right? It didn't say that. It says where do they remain the same? So they're going to remain the same anywhere temperature does not change. So if you look right here on our phase changes, at our melting and freezing, at our vaporization and condensation, our temperatures are not changing. That is where our particles are going to remain the same motion. Therefore, our kinetic energy is staying the same. All right. The lines where we have solid phase, we are increasing or decreasing temperature. So the kinetic energy is changing. They're either speeding up or they're slowing down, right? Moving on to the next one. This one says, where do all three states of matter exist? This graph that you're looking at, this is called a triple point graph, and it's really hard to get a grasp of because there's so many lines and so many things going on. But really what you're seeing is a graph divided into three different sections. You have this section here, which is all solid. Okay, anything that falls in these lines are solid. Anything that falls in these lines are liquid. And anything that falls right here in this brown section is going to be a gas. So we can look at our graph and we can determine, is it a solid, a liquid, or a gas? So the first question, where do all three states of matter exist? Well, it exists right here at what's called the triple point, where all of the lines come together and they intersect. That is the triple point. That's the only spot on the graph where they all three exist, and it's incredibly rare. Okay. Number two, if you have water at a pressure of 101 degrees for the pressure, so where you have, like, here's pressure, here's 101 degrees, right? And at negative 200 degrees, so I'll put these little lines on here for you. So, sorry, negative 20 degrees. So if we have -20, and I'm just estimating. Notice these numbers on the bottom, you guys, they don't have -20 on here. So this is just an estimation, right? So I went up from -20 to 101 for the pressure. It says, what would occur if you raise the temperature all the way to 50 degrees? It didn't say I'm changing my pressure. So my pressure is still going to be at 101. But now I need to estimate, where is 50 degrees? Well, I said it's around here. Okay, so if I go up from 50 degrees, now I'm here. So essentially I went from this spot and I traveled over here. So I was a solid and I traveled across that line and I became a liquid. So a solid traveling to a liquid is melting, right? So it would have melted and gone to a liquid phase, and that's what you can put for your answer. The next question, would you be able to boil water to make macaroni and cheese at 100 degrees Celsius at a pressure of 0.6? So we're going to go ahead and we're going to look at this. Okay, I start at 100 degrees Celsius right here. I want to go to the pressure of 0.6. So here's 0.6. So I'm going to go straight across until I hit 100 degrees. So I'm about right here, okay? So it's asking me, would I be able to boil water to make macaroni and cheese? Well, in order to boil water, I have to be liquid, right? I am now in water vapor, which is a gas phase. So I would not be able to make macaroni at this pressure. And I know you're thinking, well, 100 degrees, that's really hot. I should be able to boil some water, right? But you would have to go and be at a different pressure. See, I would have to go and cross over this line, this phase change line, in order to boil some macaroni. So at that temperature and pressure, I would not be able to. All right, thanks guys.